I'm starting the video. It's
So
okay.
now we can see the Hawaiian trees and
Oh,
everything is set.
that's all I need. The course is optional. It's the Hawaiian tree that I need. Like I
Okay,
said, it
so
was 6 in the morning and I'd be making coffee for my parents many years ago. Hawaii is beautiful.
everything is set. Just make sure to get attendance and close the lecture, and that's it. So I'm going to leave now.
All right, thank you. All right, bye-bye. And then it's just you and me, and what do we got? 42 others. All right, there'll be a few more. You'll hear the clicks. So we started.
I'm here.
Who's making all that noise? Is that you, Anvin?
The person muted his mic already.
Okay. All right, so give it a click. We started with a Turing machine last time. What I want to do, of course, is to get you guys to, some of the students would volunteer to go to the Blackboard. I'm supposed to learn how to use some software that lets me write, but I'd rather have you, the students, design some simple Turing machines. And I think Ray may have made the mistake of giving you the answers to all the homework too early. If that's the case, I'll give you different Turing machines that I would like you to work on. All right, so, oh my God, I guess this is from chapter 5. I was putting keywords on unary number theoretic functions. So number theoretic, that means we're dealing with the natural numbers. Okay. Unary, 1 to the n. All right. Function computation paradigm. Oh, symbol manipulation, language recognition. Oh, yeah, we'll certainly go through those. In principle computability. Sometimes we say, is a problem reasonable? Is it feasible? That means you can obtain an answer to the problem in an amount of time that's less than your lifetime. That's kind of reasonable. If you tell your boss you'll have the project done in 100 years, that's not really, reasonable. He or she was expecting some results in the next hour or two, maybe overnight, but not 100 years. In principle computability means you're going to have an answer to the problem, but maybe, the universe has blown up by that time. So in principle, yeah, we can solve it. Feasibility, we can solve it, and you don't have to wait for 25 years before the answer comes back. Okay. All right, you can give it a click. We go over that. Oh, we went through the definition of a Turing machine. We'll do that as we see others. LRB, move left, move right. Oh, give me a blank. Okay. And we said every textbook's going to have a different set of notation, a different notation for defining a Turing machine. We said your book, Taylor's book, and again, since it's free, it doesn't hurt for you to start. Don't print it out. I mean, I hope by now you don't print all that because, but you could import the whole book. And like we said, as we said, you're reading chapters 0 and 1. All that math we were looking at the past few classes, that's chapter 0. And looking at Turing machine problems, that's chapter 1. So we're gonna stay with this stuff for a few classes. Then I want to keep you guys busy. Oh my God, was it your class or the other one? Somebody was complaining that they didn't have enough homework. That might have been the other class. You guys seem too smart for that. Okay. Oh, possible machine actions. Yeah, we said this. You can write any one of these symbols, A1 through AK. Move left 1 square, move right 1 square. To erase a symbol, just write a capital B on top of it, blank. Okay. And auxiliary symbols, we need them. A to the n, B to the n, C to the n. Star might be an auxiliary symbol. Or make it X, Y, and Z. So every time you see an A, write an X. Every time you see a B, write a Y. I think you got the idea. So that's like an auxiliary alphabet, an extra alphabet to help you work. Okay, Anvin, go ahead. And this is the problem we were looking at. Same number of A's and B's. And we want to use a Turing machine to determine, and again, we're solving a problem or we're recognizing a string in a language. Take your pick. Those are kind of synonymous things. Okay, where, you know, solving the problem is the same as recognizing a string. All right, so, okay, so that's it, thank you. So this is where we were last time. And you need a strategy. You need an algorithm. You want to determine, and figure 1.3.1 at the bottom, we want to know if a given string has an equal number of A's and B's. Alternately, we're trying to determine if the string we're given is in the language that we're trying to recognize. So maybe I give you a string with 1,100 A's and 1,100 B's, but you don't know that. And you want to see if your the string you see in front of you with 2,200 symbols is actually in L, in the language. L of M, the language of the machine. You see that in the upper left. We always, is omega an element in the set L of M, the language that this machine was designed to recognize. Okay, we kind of started last time. And again, I gotta find out which of you is good at using these the software, so that we can look at the you know, the answer one symbol at a time. Obviously with JFlap you can do that, but we want to do it a little slower than that. Okay, so we said when you have a start state, we generally have a nice big arrow. It doesn't have to be big, but there's an arrow going into 0. I said I don't like that notation, but you know, I would have written Q sub 0. Then that's state 0. That's the start state. And are there an equal number of A's and B's? I don't know. The strategy we're going to use, as we said yesterday, Monday, is cross out an A and then look for a B that you can match or cross out with it. So in Q0, I know, I see a 0 too. Scan an A. If you see an A, then the instruction tells you, if in state 0 scanning an A, overwrite the A with a star and go to state 1. That's what all of that means. That's the 4 tuple, Q0, comma A, comma star, comma 1. So you kind of know. And again, if your machine is smart enough to walk and chew gum, you would have a 5 tuple where you could write and move at the same time. And what that would mean is that your program would be shorter. Okay, if you have more instructions, you know, a reduced instruction machine, the instructions accomplish less, so your program is going to be longer. That kind of makes sense. When you take architecture, I'm sure Professor Gertner, Professor Pong, whoever you take it with, they'll explain RISCs, reduced instruction, you know, machines. Okay, you saw an A, you crossed it out with a star, you went to state 1. Now you just wrote a star. You know, you see it just above the A. Good. So you're leaving, well, you're not leaving state 1 yet, but you're in state 1, scanning a star, go to the right. Okay, so now you're in state 3. And notice, like I said, think of it as an if statement and a while loop. That'll get you through this cryptic notation. It'll begin to seem more natural for us. So in state 3, you can read it like this. While you're still scanning a star, or while you're scanning a star, then move to the right. And keep going. And as long as you keep seeing stars, move to the right. Okay, maybe there were 10,000 stars, which meant that you processed 10,000 A's already. I don't know how many, but you need a B to match the A. That's what we're looking for. So see an A, stay in state 3, and keep moving to the right, blah, 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 blah. Finally, you see a B. There you are. We did this Monday. See the B, which is going to match the A that caused you to leave state 0, way back at the beginning. Rewrite the B as a star. And now in state 5, move to the left. You see a star, go left. You see a B, go left. You see an A, you know which way you're moving. And eventually, you're going to get to the beginning of the tape. And at the beginning of the tape, what the hell is going on at the beginning? There's a blank, a B. That's how we have a left end marker. How do you know where you started? So that's way at the left end of the tape. Most Turing machine, in most textbooks, the beginning of the tape is at the left end. Don't cry if you get a textbook someday where you begin at the right end. I've used those as well. So get to the blank, the capital B at the left end, and suppose we see a B. When I say B, I always mean little b. Capital B is not a B. Capital B stands for blank. So see a B, go down and to the right. See a B, cross it out with a star. And please go to state 2. So all of that was one instruction. You see a star. Why do you see a star? Because you just wrote one. You crossed out the B with a star. Okay, so that's like the auxiliary alphabet. The stars are helping us to cancel A's and B's as we go along. All right. See a star? Of course you see a star. You know why now. You're in state 4. See more stars, see more B's, keep going. And now you just crossed a B at the beginning of this trip, right? Now you're traveling through, I don't know, we're somewhere in California and we're going down Route 66. Hold on. Give me a second, guys. I'll be right there. Hello? That's me. Oh! I got to call the doctor to change it? Oh, I'm in the middle of a class teaching remotely. Could you put the phone call in now? Because we're doing theoretical computer science, but if you could call him, I would tell him. And you're there until what time? All right, I'll do it a little bit later. All right, thank you. No, okay, he's a tough doctor. All right, thank you. All right, bye. All right, bye-bye. Sorry, guys. My pharmacist and my doctor are dueling with each other. Okay. So yeah, I think by now you get the idea. We've done this, the string is length 1,000. We made 500 trips around this. We went the northern route, we went the southern route. When I hitchhiked across the country when I was an undergrad, I went from, I spent the summer in University of Madison, University of Wisconsin at Madison. And after the semester was over, I didn't want to come home, so I ran out to the West Coast. Then when I was coming back, I took the southern route. So here, your Turing machine goes north, Interstate 80. On the way back to the start state, it's going south, Route 66. And eventually, all the A's and B's have been starred out. And now you come back into state 0, and there's no A's and B's to be found. You processed all of them. So now when you hit the left end, it's a blank. When you see a blank, we said you go left, you're in state 6. We said Taylor, the author, is very fastidious. He likes to stay neat. So I think of it as a dance step from state 6 to 7. You're in state 6, you're seeing a star. that's all you got now is stars when you finished your processing. See a star, blank it out so it looks pretty. Now you're back in state 6, you see a blank, go, wait a minute. See a star, blank it out. Now you see a blank because you just wrote it, go left, yeah, and keep circling. And eventually you get to the left end where there's a blank. Now careful, the blank is here, you're in state 6 and you're seeing a blank. The reason you see a blank is because you got your broom out and you swept up all these stars. So you're gonna make the trip from state 6 to state 8, and you're putting down a B, blank, but it's not a blank that was there earlier. This blank you saw and you put a 1. Most books, you're not gonna put YES, the string, yes, the string is in the language. We don't wanna, one cell, we wanna write one item. So 1, if you put 1, going from 6 to 8 on an otherwise blank tape, what that means is yes. What the heck was the question? Is the string that you just processed, what do we say, 1,000 A's and B's? If it actually was an equal number of A's and B's, we're saying yes, the string is in our language. Now, 1 second.
Hey, Professor.
Go ahead. What's the, we didn't get to, we talked deciding and accepting, I think when it came to ice cream and kids, we didn't do it yet with languages. Go ahead.
Yeah, regarding the homework.
Hold on. Who is this?
Ismail.
Oh, Ishmael.
Yeah.
It really Ishmael. You're really from the Moby Dick book. I thought we changed your name. Okay, all right, Ishmael.
Okay. The homework from chapters 0 and 1 do we have to submit that to you, or is that for?
Oh my God, no! I thought I said that the first day. I never collect homework unless I tell you in advance. There's going to be some homework, but I would tell you it's not the problems in the book. I would like some of you to save me some trouble, because even when we have a real world again, I'd like to send my students to the blackboard so I can relax. And yeah, I would ask you to do one of these. And I don't want to, what do we have, 47 students? With me it's 48. I don't want to look at 48 copies of the same thing. I'd go out of my mind. I'm already crazy enough. That doesn't help me, and it's not going to help you. When I started teaching, I had to ask myself, what's my function here? Is it to make you do the homework, or is it to encourage you to learn? And I decided my job is not to make you learn. If you don't wish to, you can always take this course again. That's my attitude. If you like it and you want to learn about it, do the homework. If you think this is like reading, the comics, and you just look at it once and you understand it, then when you see the midterm, you'll be in for a shock. But that's okay. Shocks are good sometimes. Did I answer your question?
Yeah, you did.
All right, Ishmael. Yeah, always say your name first, please. It makes this course more human for me. Oh, I see, Ishmael, you're third one down. Again, Ray told me if I put all your, icons for everybody, then there's no room for the PowerPoints. We got to shrink it so I can see your faces. I don't know, but okay. So you write a 1, and in this context, the 1, everything, there are only blanks on this tape except for 1, 1. And the way Taylor would say that, you write 1 on an otherwise blank tape. And what that 1 means is yes. And what was the question? Is the string that we just processed, is it in the language of this machine, L of M? Did you just scan a string with an equal number of A's and B's? And the answer is yes. That's why you see 1. You're in state 8. The string is thoroughly processed. And what does the 1 mean? The 1 means yes. What the heck is the yes answering? The question of, does this string consist of an equal number of A's and B's? Okay, I think we're good now. Anvin, take us to the next page. I think, okay. Yeah. So here we're giving an example, ABBA, and I'm not going to go through that in slow motion. That would, blow my brain up. But we'll talk about it. Scan an A, go to the right, go past the first B, past the second. Shame on me. After the A, you change it to a star, you move to the right, you see a star, go to the right, you see a B, right? Going with his slow instructions. Scan the B, turn it into a star. See a star, move to the right, see a B, change it to a star, move to the right, you see a star, move right again, you see an A, change the A to a star, then go clean up the stars, bing, 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 however you sweep. And now, before you leave the room, you should be nice enough to write a 1 on an otherwise blank tape. Observe at the bottom, tape cleanup. You're in Q8, and there's only a 1. Well, there's 1 and a bunch of blanks. And so what did we glean from this? The string ABBA is in L of M. It's a string that has an equal number of A's and B's. So, okay, c'est tout, that's it. So again, you don't want to throw your laptop away and start using Turing machines. Theoretical computer science, we don't use this machine to replace our laptops, but we want to know what's the capability. What are the limitations of our laptops? What are they good for? That's why we do this. And we're hoping if we do this well enough, we're going to understand what the heck computers can do and what they can't do. And we'll get some insight on what the limitations are. All right, peace. Anvin? Oh, okay, so these are some more questions for us. And what are we supposed to do? Omega equals A. Somebody tell me what our Turing machine does. I need help. We won't bother you again, Ishmael. Lifu, are you Mr. Tao?
Yes.
All right, what do we do if Omega, on that Turing machine tape, we have a single A. What does the machine do?
B?
No, it's got a single A. Where'd you get B from? There's no B. The first
I
string
thought we're
is
doing like the same number of A's and B's, right?
And the question is, what if Omega equals A? Those are 4 other questions later. Don't answer those.
Oh.
If Omega equals A, what does our machine do?
This is Q. It's gonna go right, and it's gonna replace A with a star and go to Q1.
And then what?
It's gonna go to 3. Q3.
No, wait. Doesn't it answer no?
Yeah, it answers no, right? Because
No. I always tell my students, never believe any answer I give you.
So it's just gonna keep
I'm
going
always
to Q3,
trying to
right?
make it wrong. Trust me, I know the answer, but I don't want to give it to you. Shame on you. You can't say no. An acceptor for a machine never says no. If the answer would be no, in the real world, not the theoretical world, then we would fail to say yes. But you're not allowed to say no. This is a Turing acceptor. Did I read it wrong? Go back to Anvin, go back to the beginning. What is this? One more. Oh, again? Go back again? No. All right, I guess it didn't tell us. Go back to where we were. There, stop. So this is a Turing acceptor. I'm assuming it is. Acceptors say yes when the answer is yes. When they don't say yes, it just means we failed to say yes, but you're not allowed to say no. If this were a decider, then you can say yes or no. Take your pick. But no, I'm saying no, but the machine didn't. So if omega equals A, the string A is not in the language L of M. Therefore, we cannot say yes. You are not allowed to say no. We'll get to deciders a little later. And I bet there we can say no. Again, an acceptor. If a Turing machine M, capital M, it's pretty, is an acceptor for some language, and you obtain a string that's in L of M, then the machine will halt with a 1 on an otherwise blank tape. And the 1 is the Turing machine's way of saying yes. This string omega equals A is not in L of M. Therefore, the machine does not say yes. But it can't say no. Be careful. It's not like mommy can have ice cream and your mother can't say no, so you know you're getting ice cream. No, that means we're not allowed to say no. That's a decider that can say yes or no. All right, I'll try to trick you some more on that. And what if omega equals B? Then still we can't say yes, but we can't say no. We just stop, and we don't know what the heck is going on. ABA, that's not an equal number of A's and B's. You can't say yes. You scan the A, change it to a star. See a star, move right. See a B, change it to a star. See the star, move right. Well, you had to move left, I know, to get back to the beginning of the string, but I don't want to go crazy. See an A, change it to a star, and then the machine does what I'm doing. You can see me with my hands up in the air, which means I don't know what the heck to do. That's what the machine does. It's flustered. ABA is not in the language. BBA, ditto. BAB, la même chose. Those were not in L of M. All right, Anjan, I think it's beginning to it won't make sense for a while, but you're beginning to understand. Hold on 1 second.
Professor?
Yes.
A quick question. So,
No.
I'm
name.
Zeal.
Wait a minute, Zeal?
Yes.
Zeal Patel.
Mm-hmm.
Northern or southern India?
Western.
Western. Wait a minute. Not Madras.
No.
All right, you won't tell me. Go ahead.
No, it's Gujarat.
Okay.
Yeah, so the right end of the tape is also marked with a B, with a blank, right? So we know that we're at the end of the tape.
It could be. You could do that. It's your Turing machine. Just tell me what the syntax is. In this copy machine, example 1.3.2, the left end is a blank, and the right end is a blank. That H just means the machine stopped. Okay, it's, yeah, the configuration. So yeah.
Okay.
So this machine, the last machine, go back on, Vin, to the beginning of the last example. Keep going. Some more. Go forward again, sorry. Yeah, stop. So this machine is, hold on, what the hell is this machine? Language recognition. Okay, so we're trying to recognize a language. The language L consists of all strings omega, such that omega has the same number of A's and B's. So this is a Turing machine to do recognition. Okay, now go forward again to where we were. Bing, bing. Stop. No, okay. So now we're doing something called transduction. If you prefer the word translation, means the same thing. So transduction, to change one string into another. Okay, so you're given the string omega. The output of this Turing machine is f of omega. And here, example 1.3.2, you see it on top. This is a copy machine. So the input on your Turing machine tape, you got a blank on the left, a blank on the right. And okay, you don't have to, you want to put a capital H, fine. That's the head of the Turing machine. So, and you see 4 ones, 1, 1, 1, 1, 1, AKA, also known as 4. So you see 4 ones on the tape. This machine is a copy machine. So you see 4 ones. When you're done, look at the middle left. You see BH 1 to the 4th, B 1 to the 4th, B. You copy the input string of 4, and now you have 8. Well, you don't have 8. You have 2 copies of 4. Okay, BH 1 to the 4th, right? That's 4 ones. Blank 1 to the 4th, blank. So you had an input of 4. You now have copied the input of 4. So you have 2 strings of 4. Okay, so this is a paradigm. Excuse me. This is transduction paradigm. So we had a machine that recognized strings earlier, if they're in a language or not. Now this machine, these circles and lines that you see marked up, maybe they're beginning to mean something. Not to me, but you guys will explain this to me as we go along. So we're in state 0, the left side there. Again, I prefer Q sub 0, but it's okay. And you see a 1 going north. Okay, so we're in California. We're trying to get away from the smoke. See a 1, write a star. Very nice. Get to state 1. You see a star. So, star colon R. That's to be interpreted as, if you see a star, which we do. We just wrote it as we were leaving state 0. So, okay, we see a star, move 1 square to the right. You're now in state 2. Okay. And every time you see a 1, keep moving to the right. Okay. Finally, you see a blank, move to the right. So what he's doing here, the author, is he's copying the input string. I don't know, it's 100 ones, it's 17 ones, whatever it is, state 0, see a 1, replace it with a star. See a star, you just wrote a star, you got to see it, you didn't move to the right. Now for the next R, no, let's pick a better letter. J copies of 1, keep moving to the right. So while the input is 1, move to the right. So that's a while statement. Keep going to the right. Eventually you get to the right end of the tape and you move to the right 1 more square. Okay. Now you're in state 3. And you want to start reproducing the string that caused this long trip to the right. So you're in state 3. You've just gone past all the 1s. Why? Because now you're taking, you're breathing out and you see a 1. This 1 occurs after a blank. The blank is a dividing line, The input string, I don't know how long the input is. Turing machines don't tell you, I have 114, 1s on my tape, and then you're going to end up with 228. It doesn't work like that. You see 1 at a time. So see a blank, move to the right. You just pass the entire input string. What's the Chinese expression? The walk of 1,000 miles begins with but a single step. Good. So we went through the long trip. You're in state 3. Now you want to go past all the 1s that you've written. right? Whatever you had, 14, what did we say, 14 ones? You're in state 3. Okay, you're going past all of them. Then from state 3 to state 4, see a blank, write a 1. Now it's time to go left, past all the ones that brought you to the right. Oh, I'm sure I'm making this very clear. All right, we'll see. When you see a blank, that's the dividing line between the input, the 14 ones, and the string that you're writing. You want all the 14 ones, but then you want 14 more ones, after that blank. That's, between states 3 and 4. Okay. And when we are done, so this is a good problem for you to do at home. When you're done, you should have 14 ones. I'm sorry. You should have a blank, followed by 14 ones, followed by a blank, followed by 14 more ones, followed by a blank. And you made a copy of the 14 ones that were input. All right. It's your job to finish this up and make sense out of the mess that I just made of it. All right, peace. Anvin? Oh my God, homework. I didn't know there was going to be homework. You didn't warn me. Hold on. Design a term. Anvin, go forward and then we'll come back if we like. Go forward again. One more time. Is that the end of it?
I think.
How come it won't go forward?
That's it. That's it for this one. That's all for lecture 6.
Ah, lecture 6. I'm thinking of the next chapter. All right, go back. So we're forced to answer one of these. I was trying to get out of it, but I got the homework. Okay, okay. The last one was too easy. Balance parentheses. This is not too easy. Design a Turing machine M that when started scanning the leftmost symbol of an arbitrary word omega over the alphabet, sigma equals left comma right. So left paren and right paren are the two alphabet symbols. Okay. So if M's tape contains left, right, left paren, right paren, left to the third, right to the first, left to the first, right to the third initially, then ultimately M will halt scanning 1 because it's being accepted. Let's see, is that right? 3, 2, yeah, it looks like it's right. So if it's scanning originally 2 left parens and 3 rights, notice what it's saying. Then M may do anything except halt scanning a single 1 on an otherwise blank tape. It's not allowed to halt with a 1 on an otherwise blank tape because that would mean it's saying yes. And it can't say yes if the string doesn't have the right format. All right. I know the problem right now. We should be doing this, and I should be using that software that I don't know how to use yet. So let's leave this. I could explain it to you, but I don't think it'll have much import for you. Give me until Monday so I can do this step by step. All right. Keep going. I guess this was lesson 6, Anvin. We got to do some of this homework, but I don't have the homework to let me write on the screen over here yet, so we're going to have to skip it. Okay, this is good. Lesson 7. Acceptors versus deciders. This is where we get to say yes, but sometimes we may want to say no. If we have a decider, we're allowed to say yes or no. Well, I mean, whichever is appropriate. Note, another way to say decider is recognizer. Let's not use the term recognizer. Decider means the answer is yes or no. And acceptor means you say yes when the answer is yes. I forgot. What do we say when the answer is supposed to be no? Somebody help. If the answer is
Not
yes, that's right, not yes. Thank you. See, that was easy. but you can't say no. All right. So suppose L equals a to the n, b to the n, and is greater than or equal to 0. So when n is 0, what string is that? So the first string, here we have L equals a to the n, b to the n. N is greater than or equal to 0. The first string in this language is?
Empty.
The empty string.
That's right. Who said empty? That voice sounds familiar. Who was that?
Saiful.
Who?
Saiful.
Saifu?
Saiful, yes. Saiful.
No, it was a woman, not you.
Oh,
You're a
don't know.
guy. No, who's that pretty lady that was talking?
Aaliyah.
okay.
Aaliyah, thank you. All right. No, you get credit too, Saiful.
I feel bad now.
No, feel lovely. It's just, look, it's not our fault. Women sound better than we do. Men, we have awful voices. Women are always melodious. So a to the n, b to the n, when n is 1, you got the string AB, and so on. Okay. An acceptor for L, let's see, we got to get this down. We'll do some homework, I promise. Well, I should get you to do some homework. An acceptor for L will answer yes when presented with a string omega, if omega equals the empty string, or omega equals AB, or omega equals a to the third, b to the third. An acceptor for L will not answer yes when presented with a string. Let's get this out of the way. 1 second. All right. Let's keep the tree. The tree is pretty. Yeah, okay. M ultimately halts scanning a 1 on an otherwise blank tape. We shall speak of M's halting is an accepting configuration. Wait a minute. All right, I got the tree. That's important. M ultimately halts scanning a 1 on an otherwise blank tape. We shall speak of M's. I like the way he talks. Very British. All right. M's halting is an accepting configuration. All right, we got it. All right, Anvin, give us a hit. Next tape. All right. Deterministic Turing machine. Determinism. I think I mentioned that the first class. Many people believe that humans have free will. When we talk about an algorithm, whatever that algorithm does next is predetermined. It's deterministic. If the procedure is permitted to guess, then you have something called non-determinism. In computer science, Non-determinism is a useful concept. Somebody just came in. Yeah, I got to get names. All right. We'll get it together. So deterministic Turing machine, that means no guessing is permitted. We're in some state, we're scanning a symbol. What we do next is you got to do it. You can't have it, don't tell me do this or do that. No. If it's deterministic, there's only one action that's permitted. All right, so deterministic Turing machine M accepts language L if M accepts all and only the words omega in L. Furthermore, we shall write L of M for the language accepted by Turing machine M. Oh, this is beautiful. So if Turing machine M accepts language L, then L of M equals L. This is like poetry. A language L is said to be Turing acceptable if there exists some deterministic Turing machine M that accepts L. Anvin, let's take it to the next, okay. So figure 1.4.1, both Turing machines, okay, accept language L equaled A to the N, B to the M, and that's of course such that, right, the vertical line, such that N is greater than or equal to 0 and M is greater than or equal to 1, okay? So both machines accept the same language, right? Yeah, you've had algorithms that solve the same problem, okay. So he says to concentrate on 1.4.1a. That's on the left side. Oh. So let omega equal b. Oh, I can't read that. It's, after a while, his writing is too pedantic. I know. I was saying something nice about him a moment ago. All right, so the machine on the left. And we're in state Q0. Okay. And one second. Where'd that come from? Wait a minute. Do we have the same slide twice, Anvin? Go back. I'm sorry. Yeah, okay, it's just a repetition. So we're in state 0, right? On the left side. Again, I said I don't like it the way he writes state 0 with just a 0. I would have liked Q sub 0. So, okay. And one second. Oh. All right, he didn't tell us. All right, so for the string A, we're in the left here, and an A comes in. Okay, so from state 0, with an A, you erase the A, and you move into state 1. Okay, and that's all we got. So suppose that's it. Then you see a blank, and you move to the right, and that's it. The string is not accepted because we did not write a 1 on an otherwise blank tape. So c'est tout. That's it. The string's not accepted. Suppose the string is AB. Yeah, let's not look at what he writes. Just consider the string little a, little b. All right. Start in state 0. We always start at the start state. And scan in A. We're on top. Erase it. You see the capital B? All right. So saw the A, erase the A, go to state 1. Okay. Well, you erase the A, which means you hit it with a blank. Okay. Now you're in state 1, and you're scanning a blank. You just wrote it. You put a blank when you erased the little a. Okay, move to the right. You got to be careful here. When I say move to the right, I don't mean look at the screen and move your eyes to the right. I mean move, what the hell do I mean? I mean move to the tape 1 square to the right. Okay, I mean, I hope that's not confusing. So you're in Q0 now, and you see a B, a little b, there you are, and you erase it. You put a blank. All right. Now we're in state 2, and we're scanning a blank. Why are we scanning a blank? Because we just erased the lowercase b. Okay. Now, in state 2, scanning a blank. Move to the right. Okay. We're in state 3. You're still scanning a blank. If all there was lowercase ab, you are now in state 3, scanning a blank. What you're supposed to do is write a 1. You're writing a 1 on an otherwise blank tape. What did the Turing machine just do? Somebody help. Did it say yes? Did it say no? Did it say nothing? I'm lost. Somebody help. And when you catch me smiling, that means I'm not really lost, but I'm trying to see if you're lost. So here we are in state 3. What should we do? I'm Vin. Did we lose audio all of a sudden?
No.
I know. But it's shocking when 47 people can be quiet at the same time. If they were sleeping, I would hear the snoring. So they're not sleeping, but they're failing to answer. Okay. Nobody wants to say it's saying yes on an, what the hell was that word? Arbitrarily long tape? I don't know. But it just said yes. Look at that. You're on the left, state 3. You're scanning a blank. Write a 1. We said 1 means yes. I know it didn't say yes, but it's not human. I know in this pandemic, we don't think we're human either. But you write a 1 on an otherwise blank tape. Therefore, the answer is yes. What the heck was the question? Is the string AB in the language that the machine you see on the left recognizes or contends with? So, all right. How about AAB? Somebody help. I want to go. And you could use the machine on the left or the machine on the right. The machine on the left has fewer states. So you could play with the one on the right at home. So I give you the string AAB. And one of you has to take me through. And again, the machine on the left is easier to contend with. So A squared B, what the heck happens? And again, you know we're starting in state 0. And the input string is AAB. I need some help. You don't even have to have a pretty woman's voice. I'll even take an answer from an ugly guy. So, are there any ugly guys out there? Was that you, Ishmael? Who's talking? It's a shame, Anvin. It would be nicer if you could see the other 46 people, but we're both in the dark, unless a few of you are hanging out at each other's homes. So we got 40, counting mine, we have 47 different houses and apartments. Go ahead. I heard the beginning of a voice.
Hi, I'm Kevin.
Who?
Kevin.
Okay, Kevin. The input is AAB. I want that machine on the left to take it through its paces. What does it do? Go ahead.
The first thing that's read is A, so it's going to turn the A to a blank.
Okay,
And so then you're at Q1, and then since we're at a blank, it's going to go right, putting it back to Q0.
beautiful.
Then now you have a blank, an A, and a B. So the next one is an A. So then that A is going to get turned to a blank. So go to Q1.
Okay,
And then that blank makes it go right. So you're back at 0.
state 0, good. Now
And
what?
then the next key is B. So then you're going to go down to a Q2.
Beautiful.
And then you, since it's then you're going to make that B a blank. And then since it's a blank, you're going to go right to Q3. And then there's no more left. So it's going to be another blank. So it's going to return 1, go to Q4.
And since there's only a 1 on an otherwise blank tape, the machine is saying what?
A yes.
And what was the question?
It was if it recognizes that language or something like
Or
that.
if the string AAB is in L of M, or yeah, recognized by this machine. All right, hopefully it begins, we're playing a game, and hopefully we understand what the heck we're saying. All right, you could do the same thing at home with the machine on the right. That machine decides the same language. Wait a minute, I'm sorry. Accepts the same language. If you want to decide, you better see some zeros somewhere on this tape. So 0 means no. What the heck was the question? By now we know what the question was. Is the given string, decided by this machine? And the answer would be no if you saw some zeros. Since there are no zeros, this machine is an acceptor. All right, Anvin, it's beginning to make sense to me. Give us a click. Okay. So now this Turing machine accepts language L, A to the N, such that N is greater than or equal to 0. Hold on, I need some more vodka. No, if I were drinking alcohol with this stuff, I'd never make it. My head would be saying no in an otherwise empty head. All right, so, okay. This Turing machine is an acceptor. Again, an acceptor says yes when a string is in the given language, and it fails to say yes when the string is not. And by the way, those are typical midterm questions. I'll give you a machine, I'll give you a string, and you tell me, what the heck is going on. All right, we'll see. So this Turing machine accepts language L, which is equal to A to the N, and is greater than or equal to 0. So epsilon can be in here. No B's permitted. There are no B's, A to the N. Epsilon, the empty string, 1A, 2 A's, a million A's. When omega is the empty string, then the tape is empty. All right, and we don't want to read all those things I don't want to read are just, input tapes. We could make up our own examples. Hold on. Oh, Q0B. All right, we'll try that one. So try omega equals AB. All right. So there we are at Q sub 0. And the input string is AB. All right. We see an A, right? There's no B yet. B would have sent you north to state 3. Blank would have sent you south to state 2. But we have A. So we're in Q0 scanning an A. We should change the A to a blank and go to state 1. All right, so now we're scanning a blank. Why are we scanning a blank? Because we just wrote it. There it is in the middle. You see it. Okay, we're in state 1. scanning a blank. All right. We should go to the right. Ah! What the heck happened? So we're now in Q sub 0. And we are scanning. Are we scanning a B? I think we're scanning a B. What the hell happened here? Yeah, we're scanning a B. And from Q0, B, again, I said B, not blank. When you see a capital B in Turing machine talk, that's a blank. Okay, so go north. You know, you processed a little b, and you're in state 3, and you're scanning a blank. Why are you scanning a blank? Because you erased the lowercase b with a blank. So you're in state 3, and you're scanning a blank. Okay. Go to the right, and okay. You're in state 4. You're scanning an A, go to state 5. You're scanning a B, move to the right. We seem to be stuck. No matter where you are, no matter where you're going, you're not getting out. Not only are you not getting out, there's nowhere to go. You're not writing a 1 on an otherwise blank tape. And if you're not going to write a 1 on an otherwise blank tape, you are not going to accept the string AB. The only way to accept the string is to write a 1 on an otherwise blank tape. Therefore, we may conclude the string AB is not in L of M, is not accepted by this machine. That doesn't mean it's rejected. It just has failed to accept. This is beginning to make sense to me. Wow, this is dangerous. All right. Suppose the string is AA. Somebody help. Process the string AA with this automaton, A squared. Where do we start? Where do we go? What do we answer? Somebody? Ishmael? Who was the woman before with the pretty voice? What was her name? Yeah, I got to get the attendance sheet. I got to get all your pictures.
Do you want me to do it again? Yes, to try.
Yeah, but hold on. This is, okay, we got the right machine. Yeah, I got to talk to Ray. He's got to send it to me. I got to have it printed out. I'll print it out. We'll see. But somebody help. AA.
With AA, it would just be going to Q1, making it blank, and then
Hold on. Wait. Where did we start?
we're starting at 0, Q0.
Always you start at the start state. Thank you. Go ahead. Give it to me again. You're in state 0, scanning an A. What do we do?
Q1 and make the A a blank.
Good.
Then you would,
What are we
So-
scanning now?
you're scanning the blank, so you would go right to Q0.
Very nice.
And then you would be scanning an A, the next A. So you would go make it a blank and go to Q1.
Okay.
Then you would be seeing a blank, so you would go right to Q0.
And now?
You'd be scanning a blank. So you would make the blank a 1, so you go down to Q2.
And that's it. And what was the answer?
The answer would be yes.
What was the question?
The question is the same as the last one, right? Seeing if it would accept.
Is what in where? Well, you
Hmm?
got to fill in. You got to fill in the what and the where. I'm asking what was the question. You got an answer of yes, but I want to know what the question was.
Wasn't it the same question to see if we accept the given string? The
Okay.
language?
Yeah, is the string A squared in L of M? All right, I can't get you. You guys are good on this. Okay, like I said, we'll have more homework later on. We'll get there. You'll see. We're going to make sense out of all this. We still got a few minutes. Hold on. Anvin, give it a hit. I think it's the same one we repeated, but yeah. Keep going. Yeah, I made a mistake in the notes. Okay. So this Turing machine decides L, A to the N. So this Turing machine is a Turing decider. Yeah, we know that. Wait, I'm sorry. Let me take it back. So look at this Turing machine, and I see 0 some places. So if you follow a path that culminates where you've read the whole string, and you end up with a 0 on an otherwise blank tape, be careful. You can't write 0 and say no. The answer would be no. If indeed there's some unprocessed portion of the tape. Okay, so now we don't fail to say yes, we actually say no. So same thing, this Turing machine decides L, you could say L or L of M, say what you like, and I can't even see your face, but we're not going to use dirty language, shame on you. So L equals A to the N, and 0 or more A's on an otherwise blank tape. Okay, let's do the one that the author gives us. So AB, we start in Q0, scan in A. We move to the right into state 1, and we erase the first symbol, which was A. Okay, then we changed it to a blank. So now we're in state 1, and we see a blank. We move to the right, and we're back in Q0. Now, wait a minute. Oh, it's a B. We scan a B. I'm sorry, I yell when I'm scared. So we scan a little B, and we go north to state 3. We change the B to a blank. Now we see a blank. We're in state 3, and we're scanning a blank. Move to the right, and good, we're there. And we see a blank, and we go to state 6, and we write a 0. Since we're writing a 0 on an otherwise blank tape, right, we processed AB, the machine is saying no. What was the question? Is the string AB in L of M? Okay, so we're good. This is a Turing decider, which means it says yes or it says no. So if it's a kid asking for ice cream, mommy, can I have ice cream? The mother can be a ice cream decider. It can say yes, you can have ice cream, or no, you cannot. If it's afraid of losing the kid's love, then it's really just a Turing acceptor. If the answer is yes, the mother says yes. If the answer is no, the mother says ask your father. All right, so acceptor versus decider. I know this seems silly to you, but it's going to have its place when we get to undecidable questions, problems that cannot be solved. This will make sense. Okay, it's a little tough. All right, so for homework, you should be looking at chapter 1 in your textbook, the first couple of sections. Read them and try some of the problems at the end. You should be able to solve these problems. So we'll have a hit at it next time. So somebody's taking attendance. Is that you, Anvin?
I already sent it.
You sent it. Good, good. You sent it to Ray, I hope.
Yeah.
All right, he'll give me a printout. All right, guys, we're good. This is Wednesday. Have a good weekend, but try to stay busy. Don't worry about your other courses. You put all your time into this one, and you can take the other courses another semester. All right, peace. Take it easy. Nous avons fini. We're done for today. All right. Thank you. Anvin.
Or something?
Yeah, you're the one who turns things off. That's you, right?
Wait, what did I do?
When the Ray always wants the lesson to be, what is it, compiled? What does he do? He wants yeah, he wants things recorded, then it needs to be processed.
How do you end the recording?
We don't want to end. What do we want to do? I don't know.
You said to turn it off. Yeah.
So I'll let you. All right, so turn it off like he asked, and if he's not happy, I'm going to tell him you did it. All right, take it easy. Have a good weekend.
I have no idea how to do it though.
All right, take care. If you got questions, hang around.
Process the chat. I'm not too sure. I never did this before.
Oh, turning it off?
Yeah.
Maybe we'll let Ray come back.
Am I supposed to? Oh wait.